The morning of December 16, 1944, somewhere in the Ardennes forest near Bastogne, Belgium, Hauptmann Werner Kessler of the 2nd Panzer Division watched through his field glasses as American positions materialized through the fog. His artillery officer was calculating firing solutions for the German 105mm FH-18 howitzers, positioned 3 kilometers behind the advance. The Americans ahead were setting up their own guns, smaller 105mm M101 howitzers that German intelligence had dismissed as adequate but unremarkable weapons. Kessler had read the reports. The American guns were lighter, more mobile, but fired conventional high-explosive shells at conventional rates, nothing his panzers couldn't handle. Then the American guns opened fire. The first shells burst above the German infantry assault column, not on impact as expected, but in the air, dozens of airbursts rippling across the tree line in rapid succession. Kessler's stopwatch recorded what happened next. 40 rounds impacted his sector in 60 seconds. Not 40 rounds total from multiple batteries scattered across kilometers. 40 rounds from a single 6-gun battery less than 4,000 meters away. The mathematics made no sense. The crew loading rate required to sustain nearly 7 rounds per minute per gun exceeded anything in his training manuals. But the rate of fire was only part of what stunned him. Every single shell had detonated at precisely the optimal height to spray shrapnel downward through his exposed infantry. There had been no ranging shots to establish fuse timing, no adjustment fire to correct for conditions. The first salvo had burst at perfect altitude, and every subsequent round matched it exactly. His assault company took 60% casualties in 90 seconds and never reached the American line. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Kessler witnessed that December morning was the combat debut of the proximity fuse, designated VT for variable time, married to the M101 howitzer, in a combination that would fundamentally alter the mathematics of artillery warfare. The Germans had indeed dismissed the 105mm howitzer as slow when comparing raw specifications. The M101 fired a 14.97 kilogram shell to 11,700 meters. The German FH-18 fired a 14.81 kilogram shell to 10,675 meters. On paper, these were peer weapons. Similar caliber, similar range, similar shell weight. German doctrine prioritized the 105mm gun for direct-fire anti-tank work and relied on heavier 155mm howitzers for indirect fire missions. But specifications, sheets measured only half the equation. They recorded what a weapon could do under laboratory conditions. They did not capture what a weapon system, crew, doctrine, and ammunition combined could actually accomplish on a battlefield where seconds determined whether infantry survived or died. The VT fuse transformed the M101 from an adequate light howitzer into something German artillery theory had never anticipated. A weapon system capable of delivering precision airbursts at rates of fire that overwhelmed enemy positions before they could respond or take cover. The story of how this transformation occurred begins not in 1944, but in the summer of 1940, when the British Army stood alone against Germany. The Luftwaffe's bombing campaign against Britain revealed a critical vulnerability in air defence. Anti-aircraft shells required time fuses, mechanical devices set before firing to detonate at specific altitudes. But setting accurate fuses for fast-moving aircraft was nearly impossible. Gunners had to estimate aircraft speed, direction, altitude, and then manually set each fuse before loading. By the time the shell reached detonation altitude, the target had moved. British anti-aircraft effectiveness hovered around 1%. It required an average of 20,000 shells to destroy a single German aircraft. British scientists understood the theoretical solution, a fuse that could sense its proximity to the target and automatically detonate at optimal range. But the engineering challenges seemed insurmountable. The fuse would need to survive being fired, withstand 20,000 times the force of gravity during launch. It would need a miniature radio transmitter and receiver that could function for the few seconds of flight time. It would need a power source, antenna, and detonation circuit, all packaged into a device small enough to fit in a shell nose. The British began preliminary research, but lacked the industrial capacity to pursue it while simultaneously fighting for survival. In August 1940, the Tizard mission brought British scientific secrets to America, including the proximity fuse concept. The United States was not yet at war, but was rapidly expanding its military-industrial capacity. American engineers at the National Defense Research Committee took the British concept and committed enormous resources to making it work. Section 128 of the NDRC, led by Merle Tuve at the Johns Hopkins Applied Physics Laboratory, tackled the engineering problems systematically. They developed miniature vacuum tubes that could withstand the shock of firing. They created electrical systems that activated only after the shell left the barrel, preventing premature detonation. They designed fuses that transmitted radio signals and detected the reflected echo when approaching a target. When the echo strength reached a critical threshold, indicating the fuse was within lethal radius, it would trigger detonation. The technical achievement was extraordinary. The final Mark 53 fuse contained 5 miniature vacuum tubes, a battery, a radio oscillator operating at 180 MHz, and a discriminator circuit that filtered out false signals. All of this fit into a package 76 mm long and 53 mm in diameter. The entire assembly had to function perfectly after experiencing 20,000 Gs of acceleration. It had to work in temperatures from -40 to +60 degrees Celsius. It had to be manufacturable by the millions. By late 1942, the VT fuse was ready for combat testing. The US Navy deployed it first in January 1943 aboard anti-aircraft batteries in the Pacific. The results were immediate and dramatic. Fleet anti-aircraft effectiveness increased from approximately 5% to 50% almost overnight. Japanese aircraft that had grown accustomed to diving through walls of shells suddenly found those shells detonating precisely when they were most vulnerable. The psychological impact on Japanese pilots was severe. They reported that American ships were deploying proximity death rays. The Army recognized the fuse's potential for ground warfare, but faced a critical security concern. If a VT fuse landed intact on enemy territory, it could be reverse-engineered. The technology was simply too valuable to risk compromising. The fuse remained restricted to naval use, where duds would fall into the ocean, or to air defense, where duds would fall behind friendly lines. It could not be used in offensive ground operations where German forces might recover an intact example. This restriction held through 1943 and into 1944. American artillery in Italy and France fired conventional impact and time fuses, while the revolutionary technology remained locked away for security reasons. German intelligence knew the Americans possessed some kind of advanced anti-aircraft fuse. Luftwaffe pilots reported unusual airburst patterns that suggested automatic proximity detonation, but German technical intelligence had no intact examples to study. They could only speculate about the mechanism. The calculation changed in December 1944. The German Ardennes offensive, what would become known as the Battle of the Bulge, created a crisis severe enough to justify releasing the VT fuse for ground combat. General Eisenhower authorized its deployment on December 18, 48 hours after the German attack began. The authorization came with strict conditions. VT fuses would only be used in defensive fire missions on Allied territory, where recovery by German forces was unlikely. Forward observers were instructed to avoid using VT rounds in areas where German counterattacks might overrun positions before duds could be recovered. The M101 howitzer was the primary platform for this new capability. The M101, designated the 105mm howitzer M2A1, had entered service in 1941 as a replacement for the obsolete French 75mm guns that had equipped American artillery in World War I. The design philosophy emphasized mobility and reliability. The gun weighed 2,260 kilograms in firing position, light enough to be towed by a 2.5-ton truck. The split trail carriage provided 46 degrees of traverse without repositioning. The vertical sliding wedge breech block opened automatically after each shot. American artillery doctrine, built around the M101, emphasized speed of response over individual gun range. A typical artillery battalion contained 3 firing batteries of 6 guns each, plus a headquarters battery with fire direction center. The fire direction center could coordinate all 18 guns on a single target or split fires across multiple targets as needed. Forward observers with frontline infantry units could request fire missions and expect shells on target within 3 to 5 minutes. The gun's design reflected lessons learned from observing European warfare. German and Soviet artillery prioritized range and shell weight. American designers prioritized rate of fire and ease of manufacture. The M101 could sustain 4 rounds per minute with a trained crew, with burst rates reaching 6 to 8 rounds per minute. The semi-automatic breech, efficient recoil system, and separate loading ammunition all contributed to rapid, sustained fire. By 1944, American industry had produced over 10,000 M101 howitzers. When VT fuses married with M101 fire doctrine, the combination created effects that transcended simple addition of capabilities. The fuse eliminated the single greatest source of delay in artillery fire missions: fuse setting. Conventional time fuses required crew members to calculate the precise flight time to target, then manually set a mechanical timer on each shell before loading. This process added 15 to 20 seconds per round. It was also error-prone. Incorrect fuse settings meant shells bursting too high to cause casualties, or impacting the ground before detonating. VT fuses required no setting. They were screwed onto shells at ammunition supply points, then loaded and fired like any other round. The fuse automatically sensed altitude and detonated at optimal height regardless of range, weather, or minor variations in muzzle velocity. This eliminated an entire step from the crew drill. More importantly, it eliminated an entire source of error. VT airbursts were consistent in a way that manually timed fuses could never achieve. The fire rate implications were immediate. An M101 crew firing conventional high explosive could sustain approximately 3 rounds per minute when accounting for fuse setting time. The same crew firing VT rounds could sustain 5 to 6 rounds per minute, limited only by the physical process of loading propellant and shells. Burst fire rates approached 7 to 8 rounds per minute. A 6-gun battery could deliver 40 to 48 rounds per minute onto a target, all detonating at optimal airburst height. The lethality mathematics were equally dramatic. Conventional ground-burst shells created casualties through fragmentation and blast, but much of the explosive energy was absorbed by the ground. Fragments flew outward in a relatively flat pattern. Troops in trenches, foxholes, or behind cover were largely protected. Artillery effectiveness against dispersed infantry was limited. It took an average of 200 conventional shells to cause a single casualty against entrenched troops. Airburst shells detonated 15 to 20 meters above ground, showering fragments downward across a much larger area. Foxholes and trenches provided little protection against overhead fragmentation. The lethal radius of a 105mm VT airburst was 3 to 4 times larger than a ground burst. The ratio of shells required per casualty dropped from 200 to 1 to approximately 30 to 1. A single battery firing VT could achieve the casualty effect that previously required multiple battalions firing conventional ammunition. German soldiers at Bastogne and across the Ardennes experienced this new reality in the most visceral way possible. Obergefreiter Hans Dietrich, of the 26th Volksgrenadier Division, recorded his first encounter in a letter smuggled out before he was killed on December 22nd. "We advanced through the forest in extended order as trained. American artillery opened fire, but we went to ground as always. Then the trees above us exploded. The shells burst in the air, showering steel fragments straight down. There was no cover. Half my platoon was hit in the first minute. We could not advance. We could not retreat. We could only die or surrender. The psychological impact matched the physical casualties. German infantry had learned through years of combat how to survive artillery fire. Go to the ground immediately. Use any cover available. Wait out the barrage. These survival techniques were useless against VT airbursts. Going to ground meant presenting your back to fragments falling from above. Cover had to include overhead protection, which was rarely available during mobile operations. The traditional German response to Allied artillery, take cover and wait, no longer worked. German commanders recognized immediately they were facing something new. Battle reports from December 18th through 22nd repeatedly mentioned unprecedented American artillery effectiveness. Units that had sustained advances against conventional artillery fire found themselves pinned down and decimated by airbursts. Casualty rates doubled and tripled. Attack momentum collapsed. Major General Heinz Kokott, commanding the 26th Volksgrenadier Division, sent an urgent intelligence report on December 20th. Enemy artillery employs a new type of shell that detonates above ground with great effect against troops in open or light cover. Casualties from this ammunition are significantly higher than from normal high explosive. Request information on countermeasures. There were no countermeasures. The only defense against VT airbursts was substantial overhead cover or avoiding areas under American artillery observation entirely. Neither option was compatible with offensive operations. The defense of Bastogne became the definitive demonstration of VT fuze effectiveness. The 101st Airborne Division and elements of the 10th Armored Division were surrounded by December 21st. German forces outnumbered the defenders and possessed superior armor. The conventional military assessment suggested Bastogne would fall within 48 hours. But Bastogne held because American artillery, primarily M101 batteries of the 377th Parachute Field Artillery Battalion and other divisional artillery units, maintained such devastating fire superiority that German attacks could not develop momentum. The 377th was commanded by Lieutenant Colonel Harry Kinnard, an airborne artillery officer who understood exactly how to maximize VT effectiveness. His 4 batteries of M101 howitzers were positioned in a tight defensive perimeter, enabling rapid shifts of fire to any threat sector. Forward observers were positioned with every company-sized unit around the perimeter. Fire direction procedures were streamlined for immediate response. When German attacks developed, observers could have VT rounds impacting within 90 seconds of initial contact. The statistics from Bastogne reveal the scale of VT expenditure. Between December 19th and December 26th, when relief forces broke through, American artillery in Bastogne fired approximately 10,100 5mm rounds. Contemporary estimates suggest 40 to 50% were VT fuses. That meant 4,000 to 5,000 proximity-fused airbursts delivered onto German formations, attacking across relatively open ground. Hauptmann Joseph Schmidt of the 77th Grenadier Regiment attacked the Bastogne perimeter from the northeast on December 21st. His after-action report, filed after he was captured on December 23rd, described the experience. We assembled in the forest at 0400 hours. At 0530 hours, we commenced the attack across open ground toward the American positions approximately 800 meters distant. We had advanced perhaps 200 meters when their artillery opened fire. Every shell burst in the air above us. Within 2 minutes, my entire first wave, approximately 80 men, was casualties. I ordered the second wave forward. They suffered the same fate. After 5 minutes, I had no effective force remaining. I ordered withdrawal, but fewer than 30 men made it back to the start line. Schmidt's experience was repeated across every sector where German forces attempted to storm Bastogne. The combination of accurate forward observation, rapid fire direction, high rate of fire from M101 batteries, and VT airbursts created a killing zone that conventional infantry assault tactics could not penetrate. German commanders tried night attacks to reduce observation effectiveness, but American illumination rounds and pre-registered defensive fires negated that advantage. They tried artillery preparation before attacks, but American counter-battery fire was faster and more accurate. The German forces besieging Bastogne included elements of the 2nd Panzer Division, Panzer Lehr Division, and 26th Volksgrenadier Division. These were experienced formations that had fought across multiple fronts. They had overcome prepared defensive positions in France in 1940. They had broken through Soviet defense lines on the Eastern Front, but they could not overcome VT-equipped American artillery defending Bastogne. The casualty rates tell the story. German units attacking Bastogne between December 19th and 26th suffered estimated losses of 40 to 60%. The 101st Airborne and attached units defending inside the perimeter suffered approximately 20% casualties. Most American casualties came from German artillery fire into the town itself. In the open ground approaches where VT airbursts dominated, German casualties were catastrophic, while American defensive positions remained largely intact. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The German artillery's response to VT fuses was hampered by the same limitations that had plagued them throughout the war. Ammunition shortages meant German batteries were rationed to minimal daily allowances. The FH-18 howitzer, their equivalent 105mm weapon, was capable mechanically, but lacked ammunition and firing doctrine to compete. German crews were still setting time fuses manually for each airburst mission, a process that consumed precious seconds and introduced errors. More fundamentally, German artillery doctrine had never emphasized the rapid massed fires that American methods perfected. A German artillery battalion operated more independently, with individual batteries supporting assigned infantry units. The concept of massing all available artillery from multiple battalions onto a single target simultaneously existed in German doctrine, but was rarely practiced with American speed and coordination. When facing the VT-equipped M101 batteries at Bastogne, German artillery found itself outranged in effective firepower by a factor of 3 or 4 to 1. The Luftwaffe's absence compounded German disadvantages. Allied air superiority meant German movements were constantly observed and rapidly engaged with artillery or airstrikes. American forward observers had clear fields of observation, while German observers had to operate under constant threat. The Germans could not concentrate forces for attacks without being detected. Once detected, VT airbursts made those concentrations catastrophically vulnerable. Oberst Ludwig Heilmann, commanding the 5th Parachute Division attacking Bastogne from the southwest, submitted a situation report on December 24th that captured German frustration. The enemy possesses artillery of extraordinary effectiveness. Their shells burst with perfect timing above our formations, causing severe losses. Our own artillery cannot suppress their fire. Attempts to mass forces for attack result in immediate and devastating enemy artillery response. Current operations are unsustainable without significant reinforcement or enemy ammunition exhaustion. Neither reinforcement nor American ammunition exhaustion occurred. Bastogne held. The broader impact of VT fuses extended far beyond Bastogne, as German forces retreated from the Ardennes in January 1945. American artillery battalions across the Western Front received authorization to employ VT ammunition in offensive operations. The security restrictions were lifted. Allied forces were advancing into Germany itself, making fuse recovery by German technical intelligence increasingly difficult. More importantly, even if Germany obtained intact fuses, they lacked the industrial capacity and time to develop countermeasures or their own proximity fuses. The Rhine crossings in March 1945 demonstrated VT effectiveness at operational scale. Operation Plunder, the British and American crossing of the Rhine near Wesel on March 23rd and 24th, employed VT ammunition as standard for artillery preparation and suppression fires. The 9th U.S. Army's artillery, comprising over 300 medium and light howitzers, fired approximately 65,000 rounds in the initial bombardment. Intelligence estimates suggest 30 to 40% were VT-fused rounds. General Major Erich Straub, commanding the 86th Corps defending the Rhine sector, experienced the bombardment from his command post on the eastern bank. His report filed on March 25th described conditions that made effective defense impossible. The enemy artillery preparation commenced at 0200 hours with unprecedented intensity. Every square meter of our forward positions received airburst fire. Communication with forward units was lost within 15 minutes. Attempts to move reserves forward resulted in catastrophic casualties from airburst shells that our troops could not effectively shelter against. By 0600 hours, organized resistance in the forward zone had effectively ceased. The combination of VT fuses with American fire direction doctrine created synergistic effects. Time on target missions, where shells from batteries at different ranges all impacted simultaneously, became even more lethal when every shell detonated at optimal airburst height. German troops experienced these missions as instantaneous walls of steel appearing from nowhere. There was no warning crescendo of incoming fire, no time to seek cover. One moment positions were intact, the next moment entire areas were saturated with fragments. Lieutenant Werner Baumann of the 180th Infantry Division defended against the Rhine crossing near Rheinberg. His account, recorded after his capture on March 24th, emphasized the psychological destruction that preceded physical destruction. At 0200 hours, the American artillery began. But this was different from previous bombardments. Every shell burst above us simultaneously. There was no gradual build-up, no ranging shots, just sudden, total devastation. My men, veterans of Russia and Normandy, broke within minutes, not from cowardice, but from the realization that survival was impossible. When the Americans crossed at dawn, we had no effective resistance remaining. Most men surrendered immediately rather than face that artillery again. The VT fuse's impact on German morale cannot be overstated. By early 1945, Wehrmacht soldiers universally feared American artillery more than any other Allied weapon system. Prisoner interrogation reports from January through April 1945 consistently identified artillery, specifically the airburst shells, as the primary factor, degrading combat effectiveness and willingness to resist. German soldiers developed fatalistic attitudes toward American artillery fire. Unlike Soviet artillery, which employed massive but relatively inaccurate barrages, or British artillery, which was methodical and predictable, American VT-equipped artillery struck with speed, precision, and lethality that felt impossible to survive. Heinrich Böhm, a Wehrmacht medical officer captured in April 1945, analyzed the psychological phenomenon in his post-war writings. The airburst shells created a specific terror different from conventional artillery fear. Soldiers could rationalize survival against normal shells by using cover effectively, but the airbursts negated all protective measures short of concrete bunkers. This created learned helplessness. Men felt their actions had no effect on survival. This psychological state destroyed unit cohesion faster than actual casualties. German technical intelligence did eventually recover intact VT fuses. The first confirmed recovery occurred in early January 1945, when Wehrmacht engineers found an unexploded 105mm shell near Sankt Vith. The fuse was carefully extracted and sent to the Heeresversuchsstelle proving grounds at Kummersdorf for analysis. German engineers disassembled the fuse and documented its operating principles with typical German thoroughness. The technical report, filed on January 18, 1945, revealed both admiration and despair. The enemy proximity fuse represents an engineering achievement of the highest order. The miniature radio components, rugged construction, and reliable operation under combat conditions demonstrate industrial and technical capabilities we cannot currently match. The fuse employs a continuous wave radio altimeter, operating at approximately 180 MHz. The reflected signal triggers detonation, when return strength indicates optimal burst height. This is achieved without any pre-setting or adjustment. The report continued with the devastating conclusion. Development of a German equivalent would require a minimum of 18 to 24 months, even with unlimited resources and priority. Current industrial situation makes this impossible. No practical countermeasure exists beyond substantial overhead cover for all exposed positions. Recommend this information be distributed to field commanders for tactical adaptation. The tactical adaptations never materialized in any meaningful way. Building substantial, overhead cover for defensive positions required time, materials, and labor that Germany simply did not possess in early 1945. The Wehrmacht was in continuous retreat, conducting fighting withdrawals across shrinking territory. There was no opportunity to construct defensive positions that could withstand VT airbursts. Even when German forces occupied prepared fortifications like the Siegfried Line bunkers, American artillery could suppress trench systems and open areas around fortified positions. The production statistics for VT fuses reveal the scale of American industrial commitment to this technology. Between 1943 and 1945, American factories produced approximately 22 million proximity fuses. This included fuses for anti-aircraft shells, 5-inch naval guns, and the various artillery calibers used by ground forces. The 105mm VT fuse alone accounted for over 5 million units produced. At peak production in early 1945, American factories were manufacturing over 800,000 VT fuses per month. This production achievement required solving manufacturing challenges as complex as the initial engineering problems. Each fuse contained 5 miniature vacuum tubes that had to survive the shock of firing. These tubes were manufactured by the millions using specialized production techniques developed specifically for proximity fuses. The Raytheon Company, Sylvania, Philco, and other electronics manufacturers converted consumer radio production lines to military fuse production. Women workers, many of whom had assembled radios before the war, now assembled weapons components that were far more sophisticated than any consumer product of that era. Quality control was critical. A fuse failure could mean premature detonation in the gun barrel, killing the crew, or it could mean a dud that failed to detonate at all, wasting the shell and potentially providing intelligence to the enemy. American manufacturers achieved failure rates below 1%, an extraordinary achievement given the complexity of the device and the production volumes involved. The cost per fuse was approximately $18 to $20 in 1944, roughly equivalent to $300 in modern currency. This was expensive compared to conventional fuses that cost less than $1, but the effectiveness multiplier justified the expense. A VT round that achieved the casualty effect of 5 or 6 conventional rounds was cost-effective even at 20 times the fuse price. German industrial capacity could theoretically have developed proximity fuses, but the timing and resource allocation made it impossible. By the time German engineers fully understood VT operating principles in early 1945, Germany's electronics industry was collapsing under Allied bombing and resource shortages. The specialized vacuum tubes required for proximity fuses demanded manufacturing capabilities and materials Germany could not spare. More fundamentally, Germany's strategic situation made investment in defensive technologies more urgent than development of advanced artillery fuses. The V-weapon programs, Von flying bombs and V-2 rockets, consumed enormous resources that might otherwise have funded artillery development. But these programs reflected Germany's strategic desperation. Long-range terror weapons offered hope of forcing Allied negotiations through civilian morale damage. Artillery improvements, even dramatic ones like proximity fuses, could not alter Germany's fundamental strategic situation. The Wehrmacht was outnumbered, outsupplied, and compressed into shrinking territory. Better artillery fuses would not change that reality. Some German engineers proposed alternative approaches to achieving airburst effectiveness. One concept involved acoustic proximity, fuses that detected sound reflections rather than radio waves. This would avoid the radio component manufacturing challenges. But acoustic fuses faced different problems, including false triggering from battlefield noise and reduced effectiveness in adverse weather. None of these alternative concepts progressed beyond preliminary development before the war ended. The rate of fire claims in the title, 40 rounds per minute, requires careful examination against historical evidence. A single M101 howitzer could not physically sustain 40 rounds per minute. The mechanical cycle time of loading, firing, and recoil recovery limited individual gun rates to 6 to 8 rounds per minute maximum. However, A 6-gun battery firing in coordinated volleys could achieve 40 to 48 rounds per minute collective rate of fire. This is how contemporary observers would have perceived and reported the fire rate, as total rounds impacting the target area per minute, rather than per individual gun. The German assessment that American 105mm howitzers were slow likely referred to early war observations before VT fuses were deployed. Intelligence reports from North Africa in 1942 and 43 compared M101 performance against German FH-18 howitzers and found them roughly equivalent. The M101 had slightly longer range but similar rates of fire when both guns employed conventional ammunition. Neither side possessed decisive advantages in the 105mm class during this period. The deployment of VT fuses transformed this calculation completely. The M101 remained mechanically identical, but its effective rate of fire increased by 30 to 40% simply by eliminating fuse setting time. More importantly, its effectiveness per round increased by 300 to 400% through consistent, optimal airbursts. The combination meant an M101 battery in early 1945 could deliver roughly 6 to 8 times the effective firepower of the same battery in 1945-43, using the same guns and similar crew sizes. German artillerists recognized this transformation when captured M101 howitzers were tested with recovered VT fuses. Tests conducted at Hillersleben in February 1945 compared German FH-18 performance against captured M101 performance, both firing with VT fuses. The report confirmed that the American gun was mechanically superior in rate of fire, achieving 5 to 6 rounds per minute sustained, compared to the FH-18's 3 to 4 rounds per minute. But the more significant finding was that VT fuses transformed both weapons into far more effective systems than either had been with conventional ammunition. The Hillersleben report concluded with an assessment that summed up Germany's artillery situation in early 1945. The American combination of mechanically efficient weapons, abundant ammunition, advanced fusing technology, and superior fire direction doctrine has created artillery superiority we cannot match with available resources. Even if we possessed equivalent weapons and fuses, we lack the ammunition, stocks, and fire control systems to employ them with American effectiveness. The artillery battle is lost. This was not defeatism but a clear-eyed technical assessment. By March 1945, German artillery battalions were rationed to 10 to 20 rounds per gun per day. American artillery battalions routinely fired 200 to 300 rounds per gun per day. When those American rounds included high percentages of VT fuses, the effectiveness disparity became 10 to 1 or greater. German soldiers on the receiving end of this firepower learned that artillery superiority determined battlefield outcomes regardless of tactical skill or fighting spirit. The final weeks of the war saw VT fuses employed in every artillery mission where they provided tactical advantage. The crossing of the Elbe River, the reduction of the Ruhr pocket, the advances into Bavaria and Austria, all employed VT ammunition as standard. German resistance collapsed not primarily because soldiers refused to fight, but because effective resistance under such artillery fire was physically impossible. General-Lieutenant Walther Wenck, commanding the 12th Army in the final battles around Berlin in April 1945, described the futility of operations under American artillery domination. We attempted to establish defensive lines and counterattack as doctrine required. But American artillery was so responsive, so accurate, and so devastating that formations ceased to exist as coherent units within minutes of engaging. The airburst shells made every position untenable. Movement in daylight was suicidal. Even night operations were suppressed by illumination rounds and pre-registered fires. We were not defeated tactically. We were simply unable to function under such firepower. The post-war assessment of VT fuse impact on the European campaign reached clear conclusions. The US Army's Operational Research Division calculated that VT fuses increased artillery effectiveness by a factor of 3 to 5 compared to conventional ammunition. This translated directly into German casualties and degraded combat effectiveness. Statistical analysis suggested VT employment shortened the war in Europe by 1 to 3 months by enabling faster advances and more complete destruction of German defensive capabilities. The British Army conducted similar analyses and reached compatible conclusions. British artillery employed American-manufactured VT fuses from January 1945 onward, with comparable results. German prisoners, captured by British forces, reported the same terror of airburst shells and the same sense of helplessness that American-facing German units described. The VT fuse's effectiveness was independent of which Allied nation employed it. The technology itself was the decisive factor. Soviet forces received some VT fuses through presetted Lend-Lease, but employed them primarily in anti-aircraft roles. Soviet artillery doctrine emphasized different principles than American doctrine, focusing on massive preparatory barrages lasting hours rather than short, violent fire missions. VT fuses offered less advantage in Soviet employment methods. The Red Army's artillery effectiveness derived from sheer volume of guns and ammunition rather than from technological sophistication or fire control precision. The comparison between Soviet and American artillery approaches illustrates an important principle. Technology alone does not determine effectiveness. The VT fuse was revolutionary, but its battlefield impact required integration into doctrinal systems that could exploit its capabilities. American artillery doctrine, with its emphasis on speed, massed fires, and responsive forward observer systems, leveraged VT fuses optimally. Soviet doctrine, which was effective in its own way, did not require or fully utilize VT capabilities. German doctrine, optimized for a different style of warfare, could not have employed VT fuses effectively, even if Germany had possessed them. The long-term influence of VT fuse technology extended far beyond World War II. The proximity fuse concept became foundational for post-war weapons development. Modern artillery fuses employ electronic height of burst sensors derived directly from World War II VT principles. Anti-aircraft missiles use proximity fuses to maximize kill probability. Even nuclear weapons employed proximity fusing to optimize airburst effects. The manufacturing techniques developed for VT fuse production accelerated the miniaturization of electronics. The rugged vacuum tubes designed to survive artillery firing led to improved tube designs for other applications. The quality control methods and high-volume production experience gained from VT fuse manufacturing contributed to America's post-war electronics industry dominance. Companies that produced VT fuses during the Tarmanexentefly War became leaders in consumer electronics and military systems in subsequent decades. The M101 howitzer itself enjoyed an extraordinarily long service life. American forces employed M101S in Korea, where VT fuses again proved decisive in defensive battles. Chinese and North Korean infantry attacks were shattered by VT airbursts in the same way German attacks had been broken 6 years earlier. The gun served in Vietnam, where its lightweight and air mobility made it ideal for fire-based defense. American forces finally retired the M101 in the 1980s, 40 years after its introduction. Dozens of nations continue operating M101 howitzers today. The gun's combination of reliability, effectiveness, and ease of maintenance made it one of the most successful artillery pieces ever designed. Total production exceeded 10,000 units. When paired with VT fuses during World War II, it became arguably the most effective light artillery system of the war, despite being dismissed initially by German intelligence as unremarkable. The dismissal itself reveals important lessons about military assessment. German intelligence evaluated the M101 based on specifications and mechanical characteristics visible through conventional testing. Range, rate of fire with conventional ammunition, and shell weight were measured and found adequate but not exceptional. What German analysis missed was the integration of weapon, ammunition, doctrine, and industrial support into a complete system. American artillery effectiveness derived from the entire system working together. The M101 was mechanically efficient, allowing high rates of fire. The fire direction center doctrine enabled rapid coordinated massed fires. The forward observer system provided responsive targeting. The industrial base supplied abundant ammunition. The VT fuse multiplied the effectiveness of each shell. No single component was revolutionary. The revolution was in integration. German artillery possessed excellent optics, precise manufacturing, and well-trained crews. But these advantages could not overcome systematic disadvantages in fire control, ammunition supply, and technological innovation. The Wehrmacht's artillery was optimized for the warfare of 1939 through 1941, where carefully planned fires supported rapid maneuver. By 1944 and 45, warfare had evolved into industrial attrition, where volume and responsiveness mattered more than individual precision. The psychological dimension of VT fuse impact deserves final emphasis. Artillery has always been primarily a psychological weapon. The majority of artillery shells fired in combat do not directly cause casualties. They suppress enemy movement, disrupt operations, and impose fear. The effectiveness of artillery depends substantially on how enemy soldiers perceive and react to it. VT airbursts created psychological effects that conventional artillery could not match. The inability to find effective cover induced helplessness. The consistent optimal burst height suggested omniscient precision. The high rate of fire prevented adaptation or counteraction. German soldiers learned through repeated experience that American artillery fire meant certain death or wounds without effective defensive options. This lesson spread through units far faster than actual casualty rates would predict. Men who survived VT barrages told others what they experienced. Units facing American artillery for the first time were already expected to be helpless against it. This psychological preparation for defeat was as significant as the physical casualties VT fuses inflicted. When German soldiers expected to be destroyed by American artillery, they were less willing to expose themselves to it. Attacks lost momentum before artillery even fired. Defensive positions were abandoned at the first sign of American forward observers. The weapon's reputation did as much work as the weapon itself. Hauptmann Werner Kessler, whose experience opened this account, survived the Ardennes campaign and was captured during the Rhine crossing in March 1945. His post-war memoir devoted significant attention to American artillery, and specifically to the morning of December 16th, when he first encountered VT fuses. "I had experienced 4 years of war," he wrote. "I had faced Russian artillery on the Ostfront, British guns in Normandy, and American conventional artillery in the fall of 1944. But nothing prepared me for what the Americans demonstrated that December morning. It was not simply more effective artillery. It was artillery that operated on different principles, that negated everything we had learned about survival, that made our tactical training obsolete. In that moment, watching those shells burst perfectly above my men, I understood we had lost the war, not because we lacked courage or skill, but because the enemy had achieved technical and systematic superiority we could not match." Kessler's realization was shared by thousands of German officers and soldiers who faced VT-equipped American artillery in the final months of the war. The experience taught a lesson that military institutions would remember. Technical innovation matters, but only when integrated into effective operational systems. Industrial capacity to produce advanced weapons in quantity matters more than laboratory prototypes. Doctrine that exploits technological advantages determines whether those advantages translate into battlefield success. The story of the VT fuse and the M101 howitzer is ultimately a story about systematic superiority. The United States developed not just a clever fuse, but an entire artillery system, from forward observers to fire direction centers to industrial production, that could employ that fuse more effectively than any other nation could have. Germany, despite possessing excellent engineers and skilled soldiers, could not match this systematic integration. The gap between German and American artillery effectiveness in 1945 measured the gap between pre-war military theory and modern industrial warfare. The shells that burst above Werner Kessler's assault column on December 16, 1944, represented more than technical achievement. They represented a philosophy of warfare based on systematic efficiency, industrial production, and technological integration. That philosophy proved decisive in World War II and defined American military capabilities for decades afterward. The Germans who dismissed the 105mm howitzer as slow learned too late that the weapon's true speed was not mechanical but systematic, measured not in rounds per minute per gun, but in effective destruction delivered faster than enemy forces could survive or adapt. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.